And in the coming next session, Professor Xiang Li, Associate Professor, Department of Automation, Tsinghua University, will introduce a new complementary framework for human-robot collaboration that balances the safety of humans and the efficiency of robots. Professor Li, please.
Okay, thank you so much. First of all, dear all, very welcome to my presentation. My name is Xiang Li from Tsinghua University. So today I'm going to say something about the collaborative human-robot collaboration. So this will be the outline of my talk. I will first start with some background. And people may know that we have some progress for the robotic manipulation. For the robotic manipulation is that the robot is trying to mimic the way how the human is manipulating things. However, in the following kind of three tasks, still there is a big gap between the human and the robot. So these three kind of tasks include the in-hand manipulation, the manipulation of a deformed object, and also the human-robot collaboration. So in this talk, I'm going to focus on the last one, which is the human-robot collaboration. So this is a typical structure of the human-robot collaboration. So we can see that there's many kind of four parts, which is the interaction, the planning part, the robot control, and also the perception part. So the human actually can pass his motion intention via the interaction part. Then for the planning part will generate the reference trajectory for the robot according to the task. Then for the perception is mainly to monitor the change of the task and also the change of the environment. Finally, the control part. Control part is going to compare the current state of the robot and also generate the command to drive the robot to serve the human. So the title of the shared autonomy is mainly included in this planning part, which we are going to provide more detail in the following talk. So firstly, I will just briefly go through some progress for the perception and the interaction. So we can see that we have a different sensing part. So for the motion capture, we can use it to measure and also predict where is the human. Then we can drive the robot to place some tool at the desired position. So the human just can go there to pick up the tool to do the assembly task. Or we can use the tiny operation on the right side to directly transfer the human motion intention to the robot. Or we have this EMG sensor. The EMG sensor can be used to measure the contraction and the relaxation of the human muscle, and then we can have a neural network to specify the human motion intention, so the robot can serve the human. Also, we have the AR or VR. We can let the human and the robot to interact in the virtual environment. So we know that the human has a lot of skillful manipulation ability, and also there are a lot of data during the human-robot collaboration. So people are thinking whether we can let the robot learn from the human. Actually, there are two kind of learning methods. One kind of method we call is the model-based learning. So for this kind of method, actually cannot be used for those complex, highly dynamic environment. Also, we have a lot of requirements for the sensing part. In addition, it's very difficult to program the human manipulation skills with the programming languages. Another kind of this learning skill, we call it learning from demonstration. But mainly the current state is we can just let the robot to learn for the end factor, not the joint configuration. So then this slide summarizes some progress for the shared autonomy. And actually the definition of the shared autonomy is to plan the robot behavior to let the robot better collaborate with the human workers. So in a human-robot collaboration system, basically we have a human control input and also a robot control input. So the shared autonomy is let the robot to change the weight between the human control input and robot control input with the self-adaptation system. Actually, older concern before this shared autonomy is this shared control. The first one is the shared control. But in the shared control, the weight between the robot control input and the robot control input cannot change. It is predefined or defined by the human. Actually, we can also see the difference for these two kind of shared in the following two equations. So in the shared autonomy, we have the theta represent the self-adaptation of the robot. This theta includes the state of the task, the robot, and also the human. And these are some applications for the shared control. As we can see, the first two applications is the rehabilitation or the human-robot collaborative drawing. So these two applications, the human-robot has the direct contact. Also, we have the application in the technique operation for the technique-operated polishing. As we mentioned before, in the shared control, all these applications, the weight between the human and the robot is fully predefined or defined by the human. The robot cannot change it by itself. And also, as we mentioned before, different from the previous shared control, we have this shared autonomy. So the shared autonomy means that the robot can automatically change the weight between the human control input and the robot control input by assessing the change of the task and also the change of the dynamic systems. So there has been some applications for the shared autonomy, as we can see, in the simulated surgical operation or in the technique operation or the collaborative coating, wiping, and sewing. So in all these tasks, the task may change or the motion intention of the human may change. So the robot should have the adaptation ability to continuously change the role according to the change. So in this talk, we think about this mixed scenario for human-robot collaboration. We consider the mixed scenario because there are two kinds of environment. So as we can see from this figure, the first environment we consider is the right interactive environment. So in this kind of environment, maybe the human and the robot work together. For example, the human can pass the scene to the robot to the placement. So in the isolated environment, which is the second environment, this kind of environment, the robot has to work by itself independently. For example, the robot has to place some dangerous things to the desired position. Also see from this figure, we can see another person is sitting away from the human and the robot. This kind of person can make the contributions to both environment. For example, he can deal with some force changes or dynamic changes to avoid the collision between the human and the robot in the first environment. Also, he can teach the robot to follow the demonstration to place the object to the desired position. And there are several challenges for this kind of mixed environment, as we have listed here. Maybe some human workers will enter the workspace of the robot. And for example, if the worker uses some sensor to do the manipulation, maybe the environment is not calibrated. So the previous existing shared autonomy cannot be used to deal with those challenges we listed before, because both the human and the robot are working in the same space, either in the drawing space or in a task space. So in this talk, we propose this complementary framework. So this kind of framework, we can see that the robot is mainly working in the task space. The robot will just interact with the human worker, pick up the object, also place the object to the desired position. Then the human is mainly working in long space to specify the interactive area where the human and the robot are going to work together. Also deal with some unforeseen changes because maybe the worker is going to enter the workspace of the robot. And this kind of decoupling can make sure that when the human get involved of the robot task, and the robot main task and any factor will not be affected. So we can say that this realizes a better balance between the human safety and also the robot work efficiency. We can also say that this kind of framework can better combine the advantages of both the human and the robot. As we given in this figure, on the left side, the robot has several advantages. For example, high repetition, high accuracy, and also the robot can work for 24 hours. And on the right side, the human also has his or her own advantages. The human has the smart decision in a very complex scenario. The human can have the strong learning ability, and also the human can adapt to new changes in a task and the environment. So then, based on the idea of the complementary human-robot collaboration, we have proposed the experimental setup for the whole system. As we can see from the figure, there is mainly a haptic device and also an AR device, high degree of freedom robot manipulator, and also another kind of sensors working in the system. So then, from the figure, we can see that the human expert can do the demonstration with both hands, and in addition, the robot can learn from the human demonstration. After the robot learns the trajectory from the human expert, the robot can also transfer the skill to other kind of task. And in the down and left figure, we can see that there is an AR display. In the AR display, there is a virtual manipulator. So the human expert can just drag the joint of the virtual manipulator to teach the robot. And also the expert can use this AR display to specify the area where the human and the robot are going to work together. So on the robot side, we propose a new global adaptive control method by using the concept of multiple feedback turns. So this kind of multiple feedback turns is to ensure that the robotic system is always stable within the whole workspace of human-robot collaboration. As we can see, the joint space feedback turns is mainly to keep the robot from the singular configurations, and the robot is going to use the sensor to deal with the task. So when the feature of the robot is outside the field of view, we can also use the second cutting space feedback to drive the robot back to the field of view. And here we don't separate the different feedback turns. Actually, we don't use any hard switching. We combine them into a unified control input and make sure that the transition between different feedback turns is smooth and continuous. And the following figure is to show that with the vision and the cutting space feedback, we can drive the robot to start from very large initial position, smoothly translate into the field of view of the camera, then reach the goal and grasp the object. Also, we have the joint space feedback to keep the robot away from the collision or the singular configurations. Also, we have this adaptive neural network. This is to deal with the uncalibrated or unknown environment in the collaboration system. So we have, we have validated the performance of adaptive controller in the experiment. So the right figure shows that the robot can start from very large initial position to transit from outside to inside the field of view, then reach the goal at the desired position, pick the object. And the left two video it actually shows the comparison without or with the online adaptation. With the online adaptation, definitely we can have a faster convergence and high accuracy in a steady state. So during the whole robot task, we can also allow the human expert to get involved. And also because the human expert get involved in a non-space, we will say this can decouple the human control input and the robot control input. Means that there is no need to stop the robot to match the human involvement. And from the right figure, we can see that we have this AR display as mentioned before. So the human can just make the contribution via this AR display. So there's a virtual robot in front of the actual manipulator. So the human just drag the joint of the virtual manipulator. Then the change will be reflected in the real robot manipulator. And also, we would like to mention that this is a unified solution. So beside the AR display, we can also use some other kind of sensory feedback, such as the haptic device or other kind of tactile sensors and so on. So the previous about the robot grasping, once the robot grasps the object, we are going to control the robot to place the object into the desired position. And to do this kind of placing path, we use the method of this dynamic motion primitive, DMP. This kind of method provides a very quick and parameterized method. So once the robot learns it, the robot will know how to transfer the manipulation skill to other kind of tasks to another desired position. As we can see, this is the illustration of the AR. So we can use the AR to change the joint configuration of the redundant joint. We can also use the AR to define the region where the human and the robot going to work together to transfer the object. So beside the AR display, also we can have the haptic device to teach the motion of the robot and effector to place the object into the desired position. So with the help of the mixed interface, the robot can learn both the motion of the robot and effector, and also how to move to the desired position in a task space. So the left video shows that is the learning phase. In the learning phase, the robot just learn how the human manipulate the things. The right video is the reproducing phase, means that the robot will just mimic the way how the human is going to place the object. So here we want to emphasize that once the robot learns the trajectory, actually the robot can deal with the different tasks because we can change the goal of the robot. We can also change the trajectory of the robot to the desired trajectory. So in all this demonstration, the robot can avoid the collision with the environment in a very similar way. Here we also demonstrate the whole pipeline of the grasping and the manipulation. So this video shows that during the robot task, there's a human worker mimicking to get into the workspace of the robot. And the expert is sitting away from the robot and the human. But the robot, the person can see that now the robot is very close to the worker. So he can get involved to use the AR display to change the redundant joint of the robot to make sure that the robot pose can match the human workers. And also during the human involvement, we can see that there is no need to stop the robot. There is no need to suspend the main task of the robot because the human involvement is completely happening in the long space of the robot. So we can ensure both the safety and the efficiency of the robot can be granted. So this slide actually summarizes the function of our mixed interface. So we can allow the expert to use the haptic device to define the trajectory of the robot and effector. We can also use the AR device to define the region where the human and the robot is going to work together. In addition, the AR device is going to adjust the redundant joint of the robot manipulator. So to make sure that when the human gets involved, there is no need to suspend the main task of the robot. We can see from the right three figures, and actually the human did inject some contributions during the human-robot collaboration, but once the human injected the control input, the end effector of the robot can remain the same, means that the robot task is not affected. So we have used this technique to ultrasound scanning robot. So this kind of robot is to allow the robot work together with the doctor to perform the scanning task. So here the novelty is that we propose a new multimodal controllers. Specifically, we have four kind of interaction mode. So in a scanning role, the robot just performing the scanning by the robot itself. Then we have a human guided mode. So in this kind of role, the robot will become passive, just follow the motion of the human. And also we have this recovery mode. So it means that the robot loses the contact with the patient. So the robot will automatically recontact the patient. And the waiting mode is just connect the different interaction mode. So we use the waiting function to do the connection between the multiple interaction mode. And because the weighting function is very smooth, so we can make sure that the transition between different interaction modes is also smooth. Actually, the transition between multiple interaction modes can seen from this video. And the purpose of the scanning is to make sure that the blood feature, the image feature is always within the field of view of the scanning machine. And during the scanning, there is some changes of the patient, but the robot can adjust its interaction more to ensure that the human is always feel comfortable, and also the image quality is also high. So this is why we can perform the task on the real human subject, and also we can validate our robot, the robot's performance on the multiple humans scanning task. And as we can see from the video, when the patient moves his body, the interaction mode may change to another one, so the doctor can get involved to deal with some foresee changes. So this can actually enhance the patient's trust to the robot. So beside the scanning robot, another application for our complementary framework is this exoskeleton. For this kind of robot, the human just wear the robot. The robot will assess the motion intention of the human, then provide assistance to let the human feel more comfortable by wearing the robot. So here we use the compact actuator to drive the robot to make sure that the interaction between the human and the robot is safe. In addition, we have other features which listed on the right. We have the autonomy detection. We also have a new motion intention model for the human. So here's some more detail for the autonomy detection. Autonomy detection means that when the human wears the robot, there might be some physical conflict between the human and the robot. For example, the human may feel fatigue, or there's an imbalance between the human and the robot. So in this case, the autonomy score will increase, and then the weighting function will decrease. The decreasing weighting function can make sure that the robot becomes passive to address those conflicts between the human and the robot. Also, we have this below dual channel estimation intention for the human. So specifically, we have a short motion intention to let the robot quickly respond to the human. And also we have this long motion intention to make sure that the estimation is very precise. And in addition, we have done a lot of experiments to test the robot. Actually, the result is shown in the right figure. This EMG sensor reading means whether the human feels comfortable. The lower of the EMG reading data means that the human will feel much more comfortable. So from the comparison, we can see that with our proposed complementary framework for the human-robot collaboration, and also with the development of the exoskeleton, we can make sure that when the people wear the robot, the people will feel more comfortable and safe. So this will be some conclusion for my talk. In this kind of presentation, we mainly propose complementary framework for the human-robot collaboration. This new framework will allow the robot to safely coexisting and work with the human workers. And also we propose a new mixed AR and haptic device to make sure that the human involvement is very convenient and intuitive. In addition, the human involvement always happens in a long space, means that the robot does not need to stop to meet the requirement of the human. And in last, we have applied this kind of a complementary framework to those different robotic systems. For example, the collaborative manipulation system, the collaborative scanning system for the doctor, and also the wearable exoskeleton robot. So we believe this kind of framework will provide a unified solution to the shared autonomy. So this will be the end of my talk, and thank you so much for your time. Thank you.